November 12th, 1942, Richmond, California. Henry Kaiser stands on the gravel lot of Richmond Shipyard No. 2, stopwatch in hand, as the last prefabricated section of hull number 440 swings into position. The welding torches ignite simultaneously across 17 stations. Sparks cascade into the grey morning air. Behind him, a delegation of British Admiralty officers checks their own watches, scepticism etched into their faces. They have flown 7,000 miles to witness what their analysts have declared impossible: the construction of a 10,500-ton cargo vessel in less than 5 days. The ship taking shape before them represents hull number 440 of the EC-2SC-1 Emergency Cargo Vessel Program, a designation that will soon be known by another name, the Liberty ship. But what these British observers cannot yet comprehend as they watch American welders work in choreographed precision is that they are witnessing not merely the construction of a single vessel, but the industrial answer to a mathematical problem that threatens to strangle Britain's war effort. At this moment, German U-boats are sinking Allied merchant ships faster than traditional shipyards can replace them. Admiral Karl Donitz's Wolfpacks have sent 1,664 Allied vessels to the bottom in 1942 alone, totaling 7.8 million tons of shipping. The arithmetic is brutal and straightforward. Britain imports 55 million tons of supplies annually, and the island nation possesses a strategic reserve of only 3 months. The German Kriegsmarine needs only to maintain this rate of destruction for another 9 months to force British surrender through starvation alone. What Dönitz and his U-boat commanders do not know is that the industrial foundations of their strategy have already been undermined by a radical transformation occurring in American shipyards. The vessel taking shape in Richmond represents the first product of a manufacturing revolution that will ultimately build ships at a rate that defies every conventional calculation of naval construction. The British observers have come to verify reports they find incredible: that American yards are now launching a complete 10,500-ton cargo ship every 42 days on average, with some yards achieving completion in under 2 weeks. If true, these production rates will transform the mathematics of the Battle of the Atlantic from a war of attrition. Germany is winning into an industrial contest that the Third Reich cannot possibly sustain. Kaiser glances at his stopwatch as the final hull section locks into place. 4 days and 15 hours have elapsed since the keel was laid. The British Admiralty officers stand in stunned silence. The SS Robert E. Peary, which will be completed and launched in another 24 minutes, has just shattered every existing record for ship construction. But more importantly, it has demonstrated that American industry has solved the fundamental problem of the war at sea: how to build merchantmen faster than submarines can sink them. The story of how American shipyards achieved this industrial miracle begins not with the Liberty ship itself, but with a desperate British requisition placed 18 months earlier, when the dimensions of the shipping crisis first became clear to planners in London and Washington. That requisition would set in motion a transformation of ship construction that would ultimately decide the outcome of the Second World War. The crisis manifests in the statistical reports arriving at the British Admiralty throughout 1940 and early 1941. In the first 6 months of 1941, U-boats and German aircraft sink 2.1 million tons of Allied shipping. British shipyards, employing traditional riveted construction methods and craftsman-based production, can build approximately 1.2 million tons annually. The mathematics project's British defeat by mid-1942. First Lord of the Admiralty, A.V. Alexander presents these calculations to Winston Churchill in March 1941, concluding his briefing with a stark assessment. Prime Minister, we are not losing the war at sea. We have already lost it. The question is whether American production can reverse the outcome before our reserves are exhausted. The American response begins with a British Maritime Commission specification designated Ocean Class. a simple, standardized tramp steamer design developed by the British shipping company J. L. Thompson and Sons of Sunderland. The design embodies pure functionality over elegance. A 441-foot vessel with 5 cargo holds capable of carrying 10,800 deadweight tons at a service speed of 11 knots. The British commission 60 vessels under the specification to be built in American yards under the Lend-Lease program. But American shipbuilders, examining the British design, immediately identify its fundamental limitation. The specification calls for traditional riveted hull construction, a time-intensive process requiring skilled labour that would take 18 months per vessel using conventional methods. The transformation begins when the United States Maritime Commission, established in 1936 to revitalize American merchant shipping, adapts the Ocean-class design for mass production. The Commission's engineers, led by naval architect William Francis Gibbs, modify the British specification to incorporate welded hull construction throughout. This single change revolutionizes the production timeline. Traditional riveted construction requires skilled riveters working in teams of 4, a heater, a catcher, a bucker-up, and a riveter. Each rivet must be individually heated to 1,900 degrees Fahrenheit, thrown from heater to catcher, positioned by the bucker-up, and driven home by the riveter with a pneumatic hammer. A skilled riveting team can install approximately 400 rivets per 8-hour shift. The hull of a traditional cargo ship requires approximately 250,000 rivets. The mathematics is unforgiving. 625 shifts of work, requiring nearly 4 months if teams work around the clock. Welded construction eliminates this bottleneck entirely. A skilled welder can lay continuous seams at speeds 20 times faster than riveting. More critically, welding requires less specialized training. The Maritime Commission establishes a network of welding schools that can train a competent welder in 6 weeks, compared to the 4 years of apprenticeship required for a journeyman riveter. This difference in training time becomes crucial as American shipyards expand from employing 75,000 workers in 1940 to 700,000 by late 1942. The vast majority of these new workers have never set foot in a shipyard before. The welding revolution makes their rapid integration possible. The redesigned vessel receives its designation, EC2SC1. The code specifies an emergency cargo vessel, second design, propelled by a steam engine, built to Commission Specification 1. The Maritime Commission orders the first 14 vessels in December 1940, distributing contracts across multiple American shipyards to establish production capacity. But the real innovation lies not in the design itself, but in the production methodology that will build these ships. The revolution in production begins at the Bethlehem Fairfield Shipyard in Baltimore, where yard manager Joseph L. Powell implements a system of prefabrication that transforms ship construction from a sequential process into a parallel manufacturing operation. Traditional shipbuilding lays the keel, then constructs the hull frame by frame from the keel upward, then installs deck and bulkheads, then outfit the interior. Each stage must wait for the previous stage to complete. Powell's innovation divides the ship into 250 prefabricated sections constructed simultaneously in fabrication shops away from the building way. These sections, weighing up to 170 tons each, include not only steel frames, but pre-installed piping, wiring, and ventilation systems. The prefabricated sections arrive at the building way ready for final assembly, reducing the time the hull occupies the critical building way from 6 months to 42 days. The mathematics of this transformation cascades through the entire production system. A traditional shipyard with 4 building ways can complete 8 vessels annually. The same yard, converted to prefabrication methodology, can complete 40 vessels annually. This five-fold multiplication in productivity comes not from working faster, but from restructuring the work so that the building way, the critical bottleneck, spends minimal time occupied by any single vessel. The comparison is stark. In 1940, American shipyards employing traditional methods produce 528,000 tons of merchant shipping. By 1943, employing prefabrication, they produce 19.2 million tons, a 36-fold increase. The first EC2 vessel, the SS Patrick Henry, slides down the ways at Bethlehem Fairfield on September 27, 1941. President Franklin Roosevelt, attending the launch, coins the name that will supersede the technical designation. This ship, Roosevelt declares, is one of a new class of ships which will eventually constitute the largest merchant fleet under one flag. They will carry goods to all parts of the world and will represent American productivity and ingenuity. Invoking Patrick Henry's Revolutionary Era Declaration, Roosevelt christens the vessel class Liberty ships. The name captures both patriotic sentiment and functional purpose. These ships will carry the material that preserves liberty across the Atlantic. But the Patrick Henry's 244-day construction time, while impressive by traditional standards, still falls short of what the crisis demands. The Battle of the Atlantic intensifies through late 1941 and into 1942. Admiral Dönitz receives authorization to expand his U-boat fleet from 91 operational boats in January 1942 to 300 boats by mid-1943. The Wolfpack tactics devastate Allied convoys. In June 1942 alone, U-boats sink 144 Allied ships, totaling 700,000 tons. The American shipbuilding program faces a mathematical reality, even building Liberties in 244 days. Production cannot overcome the rate of loss. The margin for victory exists only if construction time drops below 90 days per vessel on average. The industrial solution emerges from an unlikely source. Henry Kaiser, a construction magnate with no previous shipbuilding experience. Kaiser had built the Hoover Dam and the Grand Coulee Dam, massive civil engineering projects that required coordinating thousands of workers and millions of tons of materials. In 1941, Kaiser secures maritime commission contracts to build 7 shipyards on the West Coast, the largest concentration of new shipbuilding capacity in history. Kaiser brings to shipbuilding the mass production techniques he developed in construction: detailed scheduling, parallel work streams, continuous workflow optimization, and an absolute focus on speed. At Kaiser's Richmond shipyards in California and Swan Island Yard in Portland, Oregon, the prefabrication methodology reaches its ultimate evolution. Kaiser's engineers divide the Liberty ship into 250 prefabricated sections, but go further, subdividing these into 30,000 individual component parts manufactured throughout the San Francisco Bay Area. Machine shops, steel fabricators, and electrical works receive detailed specifications for standardized components. These flow into the Richmond yards on a precisely scheduled logistics network. The shipyard itself becomes an assembly plant rather than a construction site. Workers on the building ways perform only final assembly, welding the large sections together and completing connections between pre-installed systems. The time compression this achieves is dramatic. By mid-1942, Kaiser's Richmond Yard No. 2 is completing 1 Liberty ship every 14 days on average. By November, Kaiser proposes a demonstration to silence skeptics who claim these production rates represent statistical anomalies or shoddy construction. He will build a complete Liberty ship, from keel laying to launch, in less than 1 week. The British Admiralty sends observers. The American press sends reporters. And on November 8, 1942, Kaiser begins construction of hull 440, which will receive the name Robert E. Peary. The construction of the Robert E. Peary represents the culmination of 2 years of continuous production optimization. The prefabricated sections arrive at the building way on a minutely choreographed schedule. The keel sections lock into place within the first hour. Hull sections, each weighing up to 170 tons and measuring up to 50 feet in length, swing into position every 20 minutes through the first day. 200 welders work simultaneously, their torches creating a continuous curtain of sparks. The deck sections, complete with pre-installed winches and ventilators, drop into place on the second day. The prefabricated deckhouse, containing berthing, galley and bridge, arrives as a single 80-ton unit and settles onto the deck on day 3. Engine installation, normally requiring 2 weeks, takes 16 hours as the pre-tested triple expansion steam engine and boilers slide into the prepared engine room. Electrical systems, pre-wired in the prefabricated sections, require only final connections. Piping systems, pre-installed and pressure tested, need only valve installation. 4 days and 15 hours after the keel touches the blocks, the Robert E. Peary sits complete on the building way. The launch ceremony takes 24 minutes. The vessel slides stern first into the bay, rides the water for the first time, and steams under her own power to the outfitting dock for final systems checks and load testing. 7 days after keel laying, the Robert E. Peary departs for her maiden voyage, carrying 10,500 tons of war material bound for Britain. The British Admiralty observers cable London, construction time verified. American claims proven accurate. Production capacity exceeds all projections. The record-setting pace of the Robert E. Peary represents an extreme demonstration, but the underlying production rates become standard across the Liberty ship program. By 1943, 18 American shipyards are building Liberty ships, with multiple building ways per yard. The average construction time drops to 42 days. Some yards achieve routine 30-day completions. The total production reaches staggering scale. In 1943, American yards deliver 1,949 Liberty ships, averaging 5.3 vessels per day. The mathematics has inverted. U-boats, at their peak effectiveness in 1943, sink 597 Allied merchant ships totaling 3.1 million tons. American shipyards produce 19.2 million tons of new merchant shipping, a 6-fold surplus over losses. The economic dimensions of this production contest reveal why Germany cannot win a war of industrial attrition against American manufacturing. Each Liberty ship costs approximately $2 million in 1943 dollars, including materials, labor, and overhead. The cost breaks down as follows: 10,750 tons of steel at $90 per ton, $967,500. Triple expansion, steam engine and boilers, $175,000. Electrical systems and generators, $85,000. Navigation and communication equipment, $45,000. Anchors and deck machinery, $65,000. Labor, $450,000. And yard overhead and profit, $212,500. The construction requires approximately 250,000 man-hours of direct labor, plus another 300,000 man-hours for component manufacture off-site. At prevailing wage rates of $1.20 per hour for skilled workers and 90 cents for semi-skilled workers, the direct labor cost averages $1.80 per ton of completed ship. The German Type 7C U-boat, the primary weapon opposing the Liberties, costs 4.1 million Reichsmarks to build, approximately $1.64 million at official exchange rates, but closer to $3 million, accounting for Germany's actual resource constraints and labor costs. The U-boat requires 300,000 man-hours to build, but crucially, requires workers with much higher skill levels. U-boat construction demands precision machinists, specialized welders certified for pressure hull work, and diesel mechanics capable of working to tolerances measured in thousandths of an inch. These skilled workers represent an irreplaceable resource that Germany cannot expand through training programs. By contrast, 85% of Liberty ship workers in 1943 had never worked in a shipyard before 1941, proving that the Liberty ship production system can utilize semi-skilled labor effectively. The resource calculation extends beyond simple construction costs. Each Liberty ship requires 10,750 tons of steel. American steel production in 1943 reaches 88.8 million tons annually. Building 1,949 Liberty ships consumes 20.9 million tons, approximately 24% of national steel production. This represents a massive allocation, but one that American industry can sustain while simultaneously building 45,000 aircraft, 30,000 tanks, and 8 million tons of naval vessels. Germany's steel production in 1943 reaches only 34.6 million tons, and this must support not only U-boat construction, but also tank production, aircraft manufacture, munitions, and infrastructure repair under Allied bombing. The mathematics of resource allocation leaves Germany unable to expand U-boat production beyond 270 boats delivered in 1943, while America simultaneously builds merchant ships and an enormous anti-submarine warfare fleet. The operational reality of these economics becomes apparent in the crew accounts of both Liberty ships and U-boats. On the bridge of the Liberty ship Jeremiah O'Brien, during a March 1944 convoy crossing, Captain E.J. O'Hagan maintains a philosophical perspective on the vessel under his command. "She's not fast, not pretty, not comfortable," he records in his log, "but she's honest. Everything aboard works. The engine never fails. The pumps never quit. When a torpedo hit us, yes, hit us, on the starboard side last November, the welded hull plates flexed but didn't rupture. The crew patched the hole with timber and concrete, and we made port in Iceland 3 days later. The ship is still in service. That's all that matters in this war." The O'Brien's survival after torpedo damage illustrates a crucial but unexpected advantage of welded construction. Critics of welding, particularly traditional ship architects, warn that welded hulls will prove brittle and susceptible to catastrophic failure. Riveted construction, they argue, provides superior damage tolerance because each riveted plate remains independent. A torpedo hit might rupture one plate, but adjacent riveted plates contain the damage. This theory proves partly correct, but overlooks a critical reality. Most Liberty ships hit by torpedoes survive. Of 2,710 Liberty ships built, U-boats sink 200 by torpedo, but another 67 survive torpedo hits and reach port. The survival rate of 25% for torpedoed Liberty ships far exceeds pre-war predictions that any torpedo hit would prove fatal to a merchant vessel. The unexpected durability arises from the Liberty ship's conservative design and robust construction. The hull plates are 5/8 inch steel, thicker than minimum requirements. The double bottom extends for the full length of the cargo holds, providing protection against mine damage and additional flotation if the hull is breached. The 5 cargo holds include watertight bulkheads that can be sealed rapidly, limiting flooding. Most critically, the ship carries no cargo that will explode when wet. Liberty ships transport ammunition in specially secured holds with flooding systems, but the vast majority of cargo is non-explosive. Food, vehicles, fuel in sealed drums, steel, lumber, and general supplies. A torpedoed Liberty ship typically remains afloat long enough for the crew to launch boats and for escorts to arrive. The rescue rate for Liberty ship crews exceeds 90%, dramatically higher than crews on tankers or ammunition ships. From the perspective of U-boat commanders, the appearance of Liberty ships in increasing numbers transforms the nature of the Atlantic battle. Korvettenkapitan Peter Kremer, commanding U-333 during the 1943 convoy battles, later writes, "In 1942, sinking an Allied merchantman felt like striking a blow against the enemy's capability. Each ship sunk meant months of construction effort wasted, thousands of tons of cargo lost. By mid-1943, the psychological effect inverted. We would sink a freighter, watch it go down, and see two more in the convoy that looked identical. Surface for a few hours, and our radio operator would hear British transmissions discussing a new shipyard in California, launching ships daily. The Americans were building ships faster than we could find them, faster than we could reach them through their escorts, faster than we could sink them. The mathematics had turned against us. The German Naval High Command recognizes this mathematical reality by late 1943. A classified assessment prepared for Admiral Dönitz in November 1943 analyzes the Liberty ship production program and reaches stark conclusions. The report calculates that American shipyards are delivering merchant tonnage at a rate of 15 million tons annually, while U-boat operations are sinking approximately 2.4 million tons annually. The differential of 12.6 million tons represents an insurmountable Allied advantage. More critically, the report notes that American anti-submarine warfare capabilities are improving faster than U-boat technology can counter. The introduction of escort carriers, airborne radar, acoustic torpedoes, and improved sonar means that U-boat losses are climbing toward unsustainable levels. In May 1943, the Kriegsmarine loses 41 U-boats, representing 15% of the operational fleet in a single month. These loss rates make clear that the U-boat force cannot maintain offensive operations, regardless of how many Allied merchantmen they might theoretically sink. The German analysis identifies correctly that the Liberty ship program represents not merely a tactical response to the U-boat threat, but a fundamental transformation in the industrial basis of sea power. Traditional naval strategy held that merchant shipping represented a limited resource that required years to replace. The Liberty ship program proves that industrial powers can manufacture merchant tonnage at rates that overwhelm any plausible level of interdiction. This revelation has strategic implications that extend beyond the immediate battle of the Atlantic. The ability to rapidly manufacture cargo capacity means that modern industrial powers can sustain military operations across oceanic distances indefinitely, limited only by resource extraction and industrial capacity rather than shipping availability. The human experience of working in the Liberty shipyards provides crucial context for understanding how this industrial transformation occurred. Rosa Mitchell, a welder at Kaiser's Richmond Yard No. 3, begins work in January 1943 with 6 weeks of welding training and no previous industrial experience. Her account, recorded in a 1946 oral history project, describes the yard environment. We worked 10-hour shifts, 6 days a week. The yard operated 24 hours. When day shift left, night shift arrived. The building ways never went dark. The noise was constant. Hammers, cranes, welding torches, air compressors, diesel engines. You learned to work in that noise, to communicate with hand signals because shouting couldn't be heard over the machinery. Mitchell's description continues with technical detail. My station was hull section number 17, the aft port quarter. I welded the seams where the prefabricated sections joined. The sections arrived from the fabrication shop already formed and fitted. My job was to lay the final seams, 15 feet of continuous weld along each section joint. The specs required 3 passes, a root pass to join the plates, a filling pass to build up the weld, and a capping pass to create a smooth surface. Each pass had to meet inspection standards. We had X-ray inspection for critical seams on the hull bottom, ultrasonic inspection for deck seams, visual inspection for everything. If your weld failed inspection, you cut it out and did it again. The quality control systems Mitchell describes contradict the common perception that Liberty ships were cheap or disposable vessels. While the ships incorporated standardized designs and rapid production methods, the Maritime Commission maintained rigorous inspection standards. Every Liberty ship underwent extensive testing before acceptance. Hull stress testing, engine trials, ballasting tests, and full power sea trials. The rejection rate for completed ships ran under 2%, but component rejection rates at fabrication shops ranged from 15 to 20%. ensuring that only parts meeting specifications reached the building ways. This quality system allowed the yards to maintain construction speed while ensuring that vessels met seaworthiness standards. The workforce statistics reveal the scale of the social transformation the Liberty Ship program required. In 1940, American shipyards employed 75,000 workers, nearly all male, with an average age of 42 and average tenure of 16 years. By 1943, shipyards employed 700,000 workers, of whom 28% were female, with an average age of 32 and average tenure of 11 months. The typical worker had never worked in heavy industry before. The welding schools, operating in converted warehouses and community colleges, trained 350,000 welders between 1941 and 1944. The training program compressed years of traditional apprenticeship into 6 weeks by focusing exclusively on the specific welding techniques required for Liberty ship construction, eliminating the broader skills a journeyman ship welder would traditionally learn. This workforce transformation created social tensions and challenges. Traditional shipyard workers resented the influx of inexperienced workers who earned wages comparable to craftsmen with decades of experience. Male workers frequently rejected female workers' presence in roles traditionally reserved for men. The rapid expansion created housing shortages in shipyard communities. Richmond, California, grew from 23,000 residents in 1940 to 100,000 by 1943, overwhelming existing infrastructure. Kaiser responded by constructing entire neighborhoods of worker housing, operating bus services to transport workers to the yards, and establishing childcare centers so mothers could work shifts. These social support systems proved necessary to sustain production rates, demonstrating that the Liberty Ship program required not merely industrial innovation, but social engineering to mobilize a workforce of unprecedented size and composition. The tactical employment of Liberty ships reveals their flexibility beyond simple cargo transport. The basic Liberty ship design allowed for rapid conversion to specialized variants. The Maritime Commission developed the T2 tanker variant, modified to carry petroleum products in segregated tanks. The VC2 variant received enhanced refrigeration for troop transport, carrying up to 550 soldiers in berthing spaces converted from cargo holds. The ZEC2 variant mounted balloons and anti-aircraft guns for use as convoy escort vessels. The fighter catapult ships mounted aircraft catapults for launching fighters against German reconnaissance aircraft. These conversions demonstrated the value of standardized design. Modifications could be implemented across the entire production run by distributing revised specifications to all yards. The most unusual Liberty ship conversion produced the concrete ships of 1943 to 44. Facing steel shortages despite massive production, the Maritime Commission authorized construction of 24 Liberty ships using concrete hulls reinforced with steel mesh rather than steel plates. These vessels, designated the FC2 type, proved seaworthy and durable, though heavier and slower than steel Liberties. The concrete ships served primarily in Pacific theater cargo runs where speed mattered less than cargo capacity. The successful operation of concrete Liberties demonstrated the program's flexibility and the engineering skill to adapt the basic design to resource constraints. The Liberty ship's operational record validates the production philosophy that prioritized quantity and speed over performance optimization. Liberty ships served on every ocean and in every theater of the war. They carried Sherman tanks to North Africa, supplies to Murmansk for the Soviet Union, fuel to Pacific Island bases, and troops to Normandy. The ships operated in Arctic ice, tropical heat, and typhoons. The standardized design meant that spare parts and maintenance expertise existed at every Allied port. Engine components from one Liberty ship could be installed in any other Liberty ship, dramatically simplifying logistics. The operational statistics reveal both the ship's utility and their limitations. The designed service speed of 11 knots proved accurate, Liberty ships rarely exceeded 12 knots even under ideal conditions. This slow speed made them vulnerable to submarines and limited their tactical flexibility. The reciprocating steam engines, chosen for rapid production rather than performance, proved less fuel efficient than the turbines used on faster merchantmen. A Liberty ship consumed 66 tons of fuel oil per day at cruising speed, or approximately 6 tons per 1,000 ton-miles of cargo delivered. By comparison, faster, turbine-powered vessels achieved 4 tons per 1,000 ton-miles. However, the Liberty ship's fuel efficiency disadvantage mattered less than its availability. American oil production so vastly exceeded any other nation's that fuel economy rated lower than construction speed as a design priority. The casualty statistics for Liberty ship crews provide sobering context to the Atlantic battle. Of 2,710 Liberty ships built, German and Japanese forces sank 200. These sinkings cost 1,554 merchant seamen their lives. An additional 87 Liberty ships suffered damage from torpedo, mine, or air attack, but survived to reach port. Another 196 ships were lost to marine hazards, storms, groundings, collisions, and fires. The total loss rate of 17.8% over the ship class's service life represents significant casualties, but compares favourably to earlier merchant ship losses. In 1942, before Liberty ship mass production reached full scale, Allied merchant ship losses ran at 22% annually. By 1944, with Liberty ships comprising the majority of the merchant fleet, losses dropped to 2.8% annually. This improvement reflected both increased Liberty ship construction diluting the target pool and improved anti-submarine warfare protecting the convoys. The experiences of Liberty ship crews under attack illustrate both the ship's vulnerability and their resilience. The SS Stephen Hopkins, sailing independently off West Africa in September 1942, encounters the German armed raider Steyr and the supply ship Tannenfels. The Hopkins mounts a single 4-inch deck gun and 4 machine guns, minimal armament typical for Liberty ships. As the German ships closed to point-blank range, the Hopkins gun crew, under Ensign Kenneth Willett, engages both attackers. The unequal battle lasts 20 minutes. German 5.9-inch shells devastate the Hopkins, killing 15 crew. But Willett's gun crew scores repeated hits on the Steyr, starting fires that spread to the raiders' ammunition stores. The Steyr explodes and sinks. The Hopkins, ablaze and sinking, gives the crew time to launch boats. All survivors are rescued days later by Brazilian vessels. The Hopkins remains the only American merchant ship to sink an enemy warship in surface combat during the war. This exceptional engagement aside, Liberty ship defensive tactics emphasized evasion rather than combat. Convoy sailing provided the primary defense, placing Liberty ships under escort protection. The slow speed that made Liberties vulnerable to submarines paradoxically made them ideal convoy vessels. Their consistent 11-knot speed allowed convoy commodores to maintain formation without faster ships pulling ahead or slower ships falling behind. The standardized speed of Liberty ships simplified convoy operations significantly compared to pre-war convoys, mixing vessels of varying speeds and handling characteristics. The post-war fate of Liberty ships demonstrates their enduring utility despite wartime origins as emergency vessels. Of 2,510 Liberty ships surviving the war, 835 transferred to the Soviet Union as war reparations and military aid. The Soviets, having lost most of their merchant fleet to German attack, incorporated the Liberty ships into their commercial fleet for the next 3 decades. Another 1,051 Liberty ships found commercial buyers, primarily Greek shipping companies that purchased them at discount prices and operated them profitably into the 1960s. The remaining 624 ships entered the U.S. Maritime Commission Reserve Fleet, anchored in inactive status, but maintained for potential reactivation in future emergencies. The remarkable longevity of Liberty ships in commercial service reveals that the emergency design incorporated sound engineering that transcended wartime expedients. Many Liberty ships operated commercially for 20 years or more after the war, a service life equal to purpose-built merchantmen. The Greek shipping companies particularly valued Liberty ships for their simplicity and reliability. The reciprocating steam engines, while less efficient than turbines, proved virtually indestructible and could operate on low-grade fuel oil. The cargo hold's standardized dimensions made the ships suitable for any general cargo. The low purchase price. Greek buyers acquired Liberty ships for $150,000 to $300,000 in 1946 to 47, compared to $2 million wartime construction cost, made them economically attractive, even with higher operating costs. The strategic legacy of the Liberty ship program extends beyond the specific vessels into the transformation of naval construction methodology. The prefabrication techniques pioneered for Liberty ships became standard practice in post-war shipbuilding worldwide. The modular construction approach, building ships from large prefabricated sections assembled on the building way, proved applicable to warships, tankers, container ships, and passenger vessels. Modern shipyards in Japan, Korea, and China employ prefabrication methods directly descended from the Liberty ship program. The economic logic that drove Liberty ship construction, that parallel fabrication of components maximizes use of the critical building way, remains fundamental to efficient ship construction. The welding revolution the Liberty ship program accelerated had even broader industrial impacts. The training of 350,000 welders for shipyards created a workforce that moved into other industries after the war. Welding became standard in automotive manufacturing, aircraft construction, building construction, and pipeline installation. The welding certification standards developed for Liberty ship inspection established templates for industrial welding quality control across manufacturing. The portable electric arc welding equipment developed for shipyard use found applications in field construction and repair across industries. The statistical scale of the Liberty ship achievement becomes clear when viewing the program in aggregate. Between 1941 and 1945, American shipyards built 2,710 Liberty ships totaling 29.3 million deadweight tons of cargo capacity. This construction consumed 131 million man-hours of labor and 29.1 million tons of steel. The total program cost reached $5.4 billion. These ships delivered 75 million tons of cargo overseas during the war years, including 7 million vehicles, 140,000 aircraft, 16 million tons of ammunition, and supplies for millions of soldiers. The Liberty ships, combined with 414 faster Victory ships and 651 T2 tankers, built under similar mass production programs, gave the United States a merchant fleet larger than all other nations combined by 1945. The economic return on this investment becomes apparent when calculating the alternative costs. If U-boats had succeeded in maintaining the 1942 sinking rate through 1943 to 44, Britain would have exhausted strategic reserves by mid-1943, potentially forcing negotiations with Germany. The cost to America of a negotiated peace leaving Germany dominant in Europe would have been incalculable, requiring permanent massive military spending, isolating America economically and diplomatically, and allowing Nazi regime survival. Against this alternative, the $5.4 billion Liberty ship program cost represents perhaps the most economically efficient strategic investment of the war. The human legacy of the Liberty ship program deserves recognition alongside the technical achievements. The 700,000 workers who built these ships included hundreds of thousands experiencing industrial employment for the first time. The women who welded, riveted, and assembled Liberty ships gained industrial skills and wage-earning experience that transformed social expectations about women's work capabilities. Rosa Mitchell, the Richmond welder, continued working in industrial jobs after the war, eventually becoming a welding inspector and trainer. Her career trajectory, repeated across thousands of wartime women workers, contributed to the gradual expansion of women's participation in technical fields. The merchant mariners who crewed Liberty ships faced combat conditions without military status or combat pay. The 6,700 merchant seamen killed during the war, including 1,554 aboard Liberty ships, received no veterans' benefits until 1988, when Congress finally granted merchant mariners who served in combat zones during World War II full veteran status. This delayed recognition reflects the forgotten nature of the merchant marine's contribution, sailing unarmed or lightly armed ships through submarine-infested waters to deliver the material that sustained Allied operations worldwide. The Liberty ship program ultimately achieved its fundamental objective, building merchant ships faster than enemies could sink them. This achievement required not merely industrial innovation, but systematic restructuring of how ships were designed, manufactured, and crewed. The program demonstrated that industrial capacity, intelligently applied, could overcome tactical disadvantages. U-boats remained lethal weapons throughout the war, but the mathematics of industrial production rendered their tactical successes strategically irrelevant. For every Liberty ship sunk, American yards launched 13 more. This production differential, more than any tactical innovation in anti-submarine warfare, determined the outcome of the Battle of the Atlantic. Admiral Karl Dönitz, facing war crimes charges at Nuremberg in 1946, testifies about the U-boat campaign's failure. His assessment captures the strategic reality the Liberty ship program created. We recognize by 1943 that we could not sink ships faster than the Americans built them. The mathematical relationship was impossible. Our entire submarine force could not equal the production capacity of their shipyards. The war at sea was decided not by tactics or courage, but by industrial capacity. We could not compete. The legacy persists in unexpected places. In 2024, 4 Liberty ships remain operational as museum vessels: the SS Jeremiah O'Brien in San Francisco, SS John W. Brown in Baltimore, SS Arthur M. Huddle in Greece, and SS Hellas Liberty in Greece. These survivors provide tangible connection to the industrial achievement they represent. Walking the decks of the Jeremiah O'Brien, maintained by volunteers and still capable of steaming under her own power, conveys the reality of these ships more powerfully than statistics. The simple, robust construction, the functional rather than elegant design, the evidence of human labor in every welded seam and painted surface. These ships were built by people who had never built ships before, working at a pace that seemed impossible, achieving what experts declared could not be done. The Liberty ships prove that industrial determination, properly organized and systematically applied, can achieve what seems beyond reach. The story of the Liberty ships ultimately transcends the specific vessels to reveal a broader truth about industrial warfare. That production capacity, intelligently organized and ruthlessly applied, determines strategic outcomes more decisively than tactical brilliance or technological superiority. Germany possessed superior submarine technology, superior torpedoes, and highly trained submarine commanders. But Germany could not match American industrial capacity to manufacture merchant ships at a rate that rendered submarine warfare strategically futile. The welders in Richmond and Baltimore, most of whom had never seen the ocean before 1941, decided the outcome of the Atlantic battle more surely than the U-boat aces who received medals and fame. This reversal of traditional military heroism, that industrial workers in shipyards proved more strategically crucial than combat commanders at sea, reveals the nature of total war between industrial powers. The Liberty ship program stands as testament to this reality. Wars of industrial scale are won not by heroes, but by production rates.